Let's finish this up, shall we? Okay, Helmholtz. All right, I've already been talking about this idea that our perceptual theory is one that is necessarily indirect. That is, perceptual reality and outside reality have something that comes between, sensations. Sensations are encoding data from the world. Vision, especially, we're talking about encoding the light data into information about brightness and color, which then has to be decoded and interpreted by the brain to figure out what is the most likely, I have it written right here, what is the most likely state of affairs out there in the world that could have created that particular pattern of brightness and color. And we have looked at some illusions that have suggested that sometimes in an attempt to reach a conclusion or judgment about what is happening in the world that could have caused this pattern, that we find it possible to trick this, this whole process, right? And that helps us maybe shed a little bit of light onto how that process works. And if we could do more systematic research on illusions and how they work, we would understand some of the rules that this perceptual process relies on. And one of the things that we've seen already is that there's some data to suggest that cultural differences, which then border on experiential differences, are a big influence here, right? And so the assumption is that as we acquire particular kinds of experiences interacting with a specific kind of reality, the regularities of that reality get baked into the perceptual rules, right? And so in that sense, then, as we acquire experience, we are acquiring rules for how to interpret the sensory inputs. And we then continue to use those rules. And as the older we get and the more experienced we get, the more expert we become at interpreting the world around us, so long as the world continues to follow the same rules and patterns and regularities. If we were to somehow be transported into another reality where the rules are different, then we probably wouldn't be able to function so well, though I couldn't quite tell you what kind of reality that would be. But the idea, of course, is that we are working and functioning within a reality that does have rules that we have managed to attune to and adapt to over the course of our lifetime of experience in that reality. All of this thinking comes from this guy Helmholtz here. So he gives us a theory of perception called unconscious inference. What does this mean? Well, the inference part is what we were already talking about, right? The idea is that given a particular set of sensory patterns and data coming through any one of our five senses, we have to infer the meaning of those sensations, right? And to infer the meaning of the sensations is what I have written here again, to infer what's going on in the world that could have caused those sensations. But we're also adding in the word unconscious because, and it may seem obvious, but this happens unconsciously, right? When I receive sensory data from the world, I don't consciously sit around and reflect, oh, what's going on in the world? But rather perceptual awareness appears to be effectively immediate, right? I just open my eyes and I see things. I see dogs and cats and lamps and chairs and cars and trees, without any conscious reflection over exactly how it comes to be that I see these things. I don't really think about my sensations on any regular day, right? Nobody does that, but that's kind of what I'm asking you to do in brief, one of the assignments for the brief papers, right? So in this situation, what happens, according to Helmholtz, is that we receive this, as I'm calling it, a patchwork or pointillistic array of light intensities, psychologically meaningless sensations that are encoded by the receptors in the eye. The brain receives that data and has to interpret it. And one of the things that it's going to use as this interpretive process is past experience. But past experience comes in the form of having acquired some kind of knowledge of the rules and the regularities of the world around us that's going to help us make the best possible judgment. And the better this system works, based on the more experience that we have, then the more accurate our perceptual inferences will be, and the better we will be at being able to interact successfully with the world around us. In fact, this is relevant to some things related to learning and development. I had mentioned very briefly Piaget developmental psychology before, but one thing that you also may know if you've had developmental psychology is that people who grow up, or animals who are kept in sensory deprived environments, end up not having as much neural density in their brains, especially in the perceptual regions of their brains, and their ability to perceive and interact with the world is correspondingly impaired. So having, especially in infancy and early childhood, a very rich, stimulating environment is good for overall brain development, but that's because of the fact that the brain is trying to acquire all of this information about the world to develop the kinds of knowledge structures needed for perceptual inference. So one way to think about how this works is through the use of statistics, right? So if we suggest that perception is trying to answer this question, what's the most likely state of affairs in the world that could have caused this particular pattern of sensations, then a question of likeliness or likelihood estimation becomes very relevant. And that's a probability statement. And one way to think about this, and if you've had statistics, and I hope that you have, because then you will understand exactly what I'm suggesting here, is when you are doing inferential statistics, it's the same thing. Because here I'm talking about perceptual inference, but in statistics class, you are doing statistical inference. But they can and could be the literal, exact same thing, right? What do I mean? Well, when you are, when you have a bunch of statistical data that you've collected in an experiment, you are trying to determine to what extent your data are going to tell you something about the real world, right? You want to know if you've discovered something about human behavior, and you want to be able to say something about the probability of a certain hypothesis of regarding your data to be true or false, right? It's not literally what p-values tell us, but it's part of the logic of doing hypothesis testing, is that we want to know something about the probability of our statistics telling us something real and true about reality and maybe human behavior in a psychology experiment. So the same thing is true in perceptual inference, is that I would have some sort of statistical probabilistic knowledge of the likelihood of certain kinds of events. If I'm walking in a forest and I see something that's green, to judge it as being a leaf on a tree has a certain probability associated with it. To judge it as a green coffee cup like this one has a certain probability associated with it. One of those probabilities is higher than the others, obviously, right? And therefore, that's going to influence the perceptual inference that you arrive at, right? And that's called a prior probability. The prior probability, aka the background base rate likelihood of encountering a green leaf in a forest, is much higher than the background base rate likelihood of encountering a coffee cup, right? So we use prior probabilities. That is, past experience tells us the likelihood of certain things happening in certain kinds of situations and certain kinds of environments. We can use probability theory. One good example of probability theory comes from Bayesian statistics. So maybe if you've had probability courses and statistics courses, you would have also heard of Bayes' theorem, right? Bayes' theorem gives us the ability to predict likelihoods based on prior probabilities. Another example is a modern idea emerging in neuroscience coming from the research of Carl Friston. And Friston is using what he calls free energy minimization. Now, what is that? Well, the idea here is that free energy, we're talking here about energy in the form of what's called information theoretic free energy. And that's a difficult one maybe to parse out entirely. But what we're going to just simplify for this is to talk about surprisal. And so surprisal is the idea that if I'm trying to predict what's going to happen, I'm trying to minimize the degree to which I'm surprised, right? So if I'm walking in the forest and I'm making predictions that the green things that I'm seeing are leaves, for the most part, I am minimizing surprisal because I'm mostly going to be correct. And if I happen to encounter a green coffee mug sitting in a tree, on a tree branch, I will be surprised, right? But that kind of surprise is pretty unlikely. Now, on the other hand, if I start making some weird assumptions like these trees have a bunch of green coffee cups hanging off of their branches, I will be surprised when I approach them and discover that they're not coffee cups, but leaves. So obviously that would not be a thing that our brains are going to do, is to assume anything but leaves are hanging off of the branches of all of the trees, right? And that's a good bet. And therefore, because it's a good bet, we're going to be right more often than we are wrong. And therefore, we are minimizing surprise. And as we do so, we are minimizing the degree to which we are experiencing any extra information energy, right? And that comes in the form of what's called information entropy, right? That means variation and excess energy. It's, you know, and think of entropy in thermodynamics as just, you know, going the wrong direction here thermodynamically. So we're trying to essentially predict the future, but not like the way we normally think about it. Like, what's going to happen tomorrow, predict the future. What's going to happen 2 seconds from now, right? So as I sit here at my desk, staring at my screen, giving this lecture, I can predict what's going to happen 2 seconds from now because I predict that everything's going to be exactly where it is. My coffee cup's going to still be sitting there. My little turtle sculpture, if you remember that from before, is also still going to be sitting there. And the screen is going to be there showing the slide and everything, and it's all going to be exactly the same. I can make predictions about the next moment. And if I lean forward a little bit, as you can see me doing, I can make certain predictions about how my point of view on the scene of my cluttered, messy desk is going to change as I move forward, right? And certain things are going to come into view. Some things might go out of view as I'm trying to, as I move around. And to the extent that I can continue to predict the outcome of every single little thing that I do from moment to moment to moment, creates a certain moment to moment coherence of experiences. And each one is predictable because it's just exactly the way I would expect it, right? If suddenly the world transformed into something weird and different 5 seconds from now, that would surprise me, right? And I would not be able to understand and interpret that. And that would sort of start maximizing free energy in the brain. And it would really throw my brain for a loop. And I wouldn't be able to understand the world. And I might even end up going crazy trying to understand why the world from moment to moment to moment manages to lose perceptual coherence. In fact, can we even call that schizophrenia, possibly? Is it possibly the case? Friston is a psychiatrist, by the way, that the failure of free energy minimization, and therefore the failure to sort of maintain a coherent perceptual reality from moment to moment, is somehow underlying the hallucinatory nature of a schizophrenic psychotic state. That's maybe a big hypothesis that we're not quite ready to tackle in this research, but nevertheless, this is the sort of stuff that's implied by the free energy principle, that the brain is predicting the future moment to moment to moment. And to the extent that it always manages to work, it manages to keep the world coherent and sensible and orderly for us. And everything is nice and works. And if it didn't work anymore, all bets are off. Let's illustrate, though, how the Bayes theorem might work. This might be a little bit more concrete. So this is Bayes' theorem. The probability, I'm just going to say it all out loud. The probability of A given B is equal to the ratio of the probability of B given A times the probability of A, all divided by the probability of B. All right, so what does it all mean? Well, the probability of A given B is what we want to know, right? A is some state of affairs in the world, a tree, okay? B is the sensory pattern that we have received. So if we go back to that diagram, way back here. There we go. A is that tree out there in the world. B would be the sensations or proximal stimulus, sensations, I think, right? So my brain wants to know what's the probability of there being a tree given these particular sensations that I have received right now. And that's the same structural question as what is the probability of A given B? What's the probability I'm looking at a tree given this particular set of sensations? And so we might be able to compute a number for that, right? So let's run back to our formula here. So what's the probability of A given B? What's the probability of a tree being there given this particular sensory pattern that I'm dealing with? So in order to do this, now we're not going to prove Bayes' theorem. Take a stats and probability class to understand how to prove Bayes' theorem. We're going to accept Bayes' theorem here. So this is determined by this equation here. So first is called the likelihood, the probability that B would occur if A was present. So if there is a tree out here, what's the probability that a tree would create this particular pattern? And so that's the probability of B given A. What's the probability of there being a tree there in the first place? Well, again, if I'm hiking in the woods, the probability of there being a tree might be high. If I'm somewhere else, maybe the probability is lower. And then what's the probability of B being true? That is the sensory pattern. And so what in the world is that? I mean, what do you mean the sensory pattern is true? Well, this is kind of related to some of the things mentioned earlier in the notes when talking about so the eye being imperfect, right? Retinal images can have a variety of different distortions in them. And therefore, there can be certain uncertainties associated with our sensory patterns themselves, right? So we're going to have a little bit of uncertainty in the sensory pattern. So we're not even sure we're receiving the sensory pattern we think we are, but assuming we are, then what's the probability that a tree would cause that sensory pattern? And what's the probability of encountering a tree in the first place? And factoring all of that in, I will be able to then determine the probability of seeing a tree given this particular pattern. Now, I can also ask other questions. What's the probability that I'm looking at a dog given this sensory pattern? And it might be that the probability of it being a tree is significantly higher than the probability of it being a dog. And therefore, in faced with a choice between tree or dog, I'm going to pick tree because the p-value is that much stronger for that, right? So this is the idea of how perception works. At any point in time, the brain is kind of functioning as a Bayesian prediction engine that is trying to determine what's the likelihood that the thing in front of me is X and not some other number of different things. And so simultaneously, we could possibly calculate a whole bunch of p-values for a bunch of candidate objects. And the one that has the highest probability value is the one that quote unquote wins, and therefore is the thing that we perceive. It becomes the object of our conscious awareness. It becomes the mental construction here. As I'm going to see this now as a tree and not something else, because my prediction engine of my brain has determined that that's the best, most likely interpretation of this sensory pattern. And if it is the best, most likely sensory interpretation, and if it's correct, then if I start interacting with it on the assumption that I have seen it correctly as a tree, then all of my interactions will be coherent and make sense. And I'm minimizing surprisal and I'm minimizing free energy according to Friston's free energy principle, all right? And my brain's going to be happy about that. If suddenly the tree starts barking at me and runs away, then I'm going to think I'm crazy and I might go into a psychotic state. So, well, we don't want that, right? So here's just another illustration, the basic idea. So again, we're looking at this ray diagram. This is what we call this when we look at an object projected through the lens of the eye and projected to the retina. We see the light rays kind of branching out in different directions, but the lens collects them and refocuses them all down to single points on the retina. And so now we have our upside down tree. So again, what is it that I'm looking at? Is it a tree? Well, again, I have a retinal pattern, shapes and colors and so forth. And I'm going to have to turn that into a perception. Past experience will tell me what the rules of reality are. Prior probabilities and regularities and likelihoods of the world is going to help me figure out that that's actually a tree, right? And hopefully it all works. So here I'm revisiting the question of doubt, of course. Can we really ever know for sure that this system is working? Well, this is where these questions come back. And again, the idea is that pragmatically, my interactions with the world seem to work and nothing strange and weird happens. So as long as nothing strange and weird happens, then I am minimizing free energy, I'm minimizing surprisal, and that's not going to freak my brain out. And as long as that's not happening, I can maintain a coherent conscious state. If I can't do this, if everything starts, if the world becomes so unpredictable that from moment to moment to moment, reality just shifts in and out of different states and objects change and do all these weird things, then our consciousness would completely devolve into madness. And therefore, we could not have a coherent perceptual reality of any sort. So it seems to suggest that the mere fact that we maintain coherence at all is an existence proof of the fact that perception works, right? So now that essentially wraps up our introductory content here on the nature of sensation and perception and the challenge of understanding perception given sensations, and a perceptual theory that's rooted in this sensation-mediated view that is also called indirect perception, and that Helmholtz's theory of unconscious inference is really the core of most perceptual theory when it comes down to that sensation-mediated view. But there's one last thing that I want to say before we cut it here. It doesn't have to be this way. We do not have to accept a perceptual theory that is necessarily a sensation-mediated perceptual theory that is necessarily indirect, that requires the translator and all this sort of stuff. What if we changed the nature of our perceptual theory so that instead of this idea that the eye somehow reduces the input down into elementary sensations that then have to be reconstructed into a meaningful perception in the brain, what if we treat the eye as serving a different kind of purpose? And maybe its purpose is to simply respond to information in the world. So the eye is now let's abandon the idea that the eye could be something like a digital camera that's encoding pixel values of brightness and color, right? And instead, it is it's more like an antenna, and it detects patterns. And then it responds to those patterns in a way that's more analogous to the outside world. And it's a direct response to the world as opposed to an indirect mediation between our mind and the outside world, right? If this was the case, that there's information that can be directly responded to by our sensory organs, then this would minimize the need for any kind of interpretive process. This would also then imply that our ability to predict the next moment is not really driven by past experience. It's driven by the information that's available, right? And it's information that drives our ability to interact with the world. It's not past experience and inference that drives our ability to interact successfully with the world, right? There's a big fundamental difference there, right? Is it incoming information that enables everything that we do? Or is it the acquisition of a bunch of knowledge and prior probabilities that really underlies our success in interacting with the world? These are two, I think, fair to say, radically different theories of how successful behavior could be achieved. And so this is the work of J.J. Gibson and his book here called The Ecological Approach to Visual Perception, because ecological is referring to the idea that the information that drives behavior is to be found within our ecological environment, that light and sound waves and all these things, they're actually a part of our environment. We usually, when we think about the ecological niche of an animal, we just think about like the food sources and all that other kind of stuff. But the source of sensory information in terms of electromagnetic energy, light, the visible spectrum of light, and sound waves and all that other stuff, that's all part of an ecological niche as well. And we might suggest then that seeing animals and visual systems, evolved visual systems that work the way they do because of the information available for visual systems to respond to. And so this is more of an evolutionarily connected theory because of this idea that perceptual systems evolved driven by an ecological niche of information, right? And so in this view, then there's plenty of information coming in through the senses. We don't have to deal with that minimalistic sensation-based approach where seeing something green doesn't necessarily tell me whether I'm looking at a leaf or a cup or a person in a green shirt, but rather it just tells me there's more information than that, right? And the grand sum total of all the information coming in is able to be immediately part of a single coherent whole that tells me what I'm seeing, right? And what's happening here. I don't have to have all this internal processing of information anymore. So then we'll call this direct perception instead of indirect perception, right? It just totally eliminates the need for these kinds of internal processing steps. Now, you're not going to find very much about this in the textbook, but we're going to talk about this in future lectures. I want to spend some of the future lectures to elaborate some on the ecological approach, so that maybe you can have kind of a compare and contrast between these different ways of thinking about how perception might work. But for now, I think that this is enough for that. And we are now wrapped up finally of our topic number 1, the problem of sensation and perception.